Hi, and welcome to my lesson presentation for chapters 11 and 12 of Module 4. We're going to talk today about transformations and symmetries, and also congruence, constructions, and similarities. So let's get started. So first, we are discussing rigid motion. And here in this problem, problem 1, we talked about Ephraim and Devante, and they're asked to reflect, use the rigid motion of reflection for the figure on the left. And here we have our line, and it says that the line that it's supposed to reflect on is in the center of our center square. It's horizontal, and so it's a horizontal reflection. So when we think horizontal, well, let's see what Ephraim and Devante did. So if we take a look, on the right is what they came up with. And when you're looking at that, you can see that they rotated it around, right? So all they did was take that green point right here, and they spun this whole figure around, like following the pink line, the pink arch. And that's where they, if you notice their figure on the right, that's what they did. They had a 180-degree rotation, right? Because a complete circle is 360 degrees. When you go halfway that circle, that is 180 degrees. So when we analyze their picture, their diagram, we see that they did a 180-degree rotation, but that is not what the question asked for. They asked for reflection. So what do you think of when you think reflect? Well, let's go ahead and put this line in that we're supposed to reflect on. When I think reflect, the first thing I think of is my mirror every day, right? Because we see a reflection in the mirror. Well, this horizontal line should act like a mirror. So you should see the reflection either on the top or the bottom. When you look what's above the line, it should reflect down below the line. And here we're going to see this. What's in blue, you can see through it to see what we originally had. The blue is what we went to, and a better picture of that is here. So if you notice on that horizontal line, what was once on the bottom is directly on the top. So we just, it's like we literally flip that page over. And that's what we're seeing now. Okay, for problem 2, we're wanting to find a line of symmetry. They asked, do they have a line of symmetry? I'm going to go through, even if they have multiple lines of symmetry, we're going to look at those. So a shape is symmetrical if it has one line of symmetry. It can have multiple lines of symmetry, but as long as it has one, it is considered symmetrical. So let's look at this first shape. So I put a dotted line. We're going to pretend we have a piece of paper with this shape and we fold it. Is it exactly the same? When you fold it in half, both sides of the half of the fold need to meet up identically. Does this do that? No, it does not. Well, what if we fold it this way? Is that going to give us the exact same on both sides that fold? No. So this shape is not symmetrical. It has no lines of symmetry. Next, we're going to look here, and if we fold this, does it match up perfectly? Yes. What about if we fold it this way? Yes. So this is symmetrical, and it has 2 lines of symmetry. And we're going to run through these kind of quick. So that didn't work. What if we fold it this way at an angle? No, it's still not going to work. So this one is not symmetrical. Okay, now we're looking at this triangle. What about the triangle? Well, what if we fold it in half? No, that's not gonna work, right? Because one side, when we fold it in sandwich style there, it's not gonna happen. Well, what about the other way? Yes, that way works. Now remember, it only has to have one line of symmetry to be symmetrical. So this triangle is symmetrical, but oh, here we go. Did you think about this one? If we put it at an angle, when we fold it that way, across this dotted line right here, I forget and want to point on my screen with my finger. This is going to give us an exact fold. And once again, we could do it the other way. So this is a symmetrical shape. What about here? Well, we're going to do it long ways. No, that doesn't work. Well, what about now? Yes, that works. So we have one line of symmetry, therefore it is symmetrical. What about a rectangle? So we did it long ways and up and down, so horizontal and vertical. That is symmetrical. What about this triangle? Yep. Well, that way is a no. But all we needed was one line of symmetry, and it is symmetrical. Now, what about this one, right? Because this has lots of points, and you're thinking, oh my goodness, well, this is probably the easiest one because you have a variety of options on this line of symmetry. So here we go. Let's take a pick, right? If you see I'm wrong, let me know, but I've not found one yet. We have lots of options. I even added some after I put the check mark that yes, many options with the hexagon. Okay, so now I'm going to take us off of this presentation view and we're going to go down here because I had some not nice looking things when I was trying to create the animation. So we're just going to do it manually. So here we want to see, does it have a rotational symmetry? Now, with rotational symmetry, you're going to rotate it 180 degrees. If it has rotational symmetry, it will look exactly the same at 180 degrees as it did at 0 degrees, or the original figure. So let's look at this pink, and we're going to rotate it 180 degrees. What do you think? Is this symmetrical? Does this have rotational symmetry? Yes. All right, let's try the next. 180 degrees. Looks the same to me. And we're going to continue on. Is that the same? Yes. Okay, we're on a roll. Here we go. Let's go 4 for 4. 180 degrees. Does that look the same? No, that is not the same. So the triangle does not have rotational symmetry. So now we're going to go to the next set of figures. And we're going to go to the semicircle. Rotate it 180 degrees. What do you think? No, that does not have rotational symmetry. The rectangle? Absolutely. We got one. Yay! And let's go for the triangle. No, the isosceles triangle does not have rotational symmetry. This is bothering me because it's not 180. It's a little wonky. Okay, what about the hexagon? What is your guess? I'm thinking yes. And it is. We have rotational symmetry. All right, let's get back to our slideshow. Okay, so, whoa. We went black screen for a while. Okay, now we're looking at tessellations. Do not panic. This is so fun, so easy. Well, right now it is anyway. So the best way to think of this is called tiling. You'll also hear it as tiling. Think of your bathroom tile. Lots of homes have tile throughout their house. Usually you have very simple regular tiling. So what we see here, what do you notice? Well, I noticed that there are lots of triangles, correct? Equilateral triangles. So here, there's a pattern. So when we use tiling, there's repeated patterns. And with these patterns, all the points meet up. So there are no gaps and there is no overlapping, right? So here you see every face or line meets up with another line or edge. Well, then let's go to the next one. Oh, this point is our vertex. So this is the common point with our pattern. Here, what do we see? Okay, so this is a fancier tile, right? This is our octagon. Then, so what you initially see is a bunch of octagons side to side, right? They're meeting. And then if you're not careful, if all you put are octagons, you're going to have an empty space. Well, in that space, a square fits perfectly. And to show you, oh, there we go. So this black area is what we see repeated. So you have your octagons and you square, and then we could have had a square here. See, so it's octagon, octagon, square, and this pattern repeats over and over and over. And that is tiling. So in our problem, Myra was told to come up with a vertex figure. And this is what she gave us, thinking, yes, I did it, I mastered it. Let's find out if she mastered it. So what are our rules? Our figures cannot overlap, and there can be no gaps in our spacing. It has to be perfect. Oh, let me go back to this. When you're looking at these tiles, the best place to see this in person, and I've been there twice this month for National Park for field trips, is the Fordyce Bathhouse, which is now the National Park Tourist Center. Go in there and look at their floor. They have amazing, amazing tiling on the floor. Next time, hopefully for a Team Teach, I will have a picture of that. It is amazing work. And I didn't realize exactly how amazing it was until I was putting this together. Okay, so Myra's vertex figure. We can't have any spaces. We can't have any overlapping. So let's go around and put the hexagon in every other spot. So she gave us the hexagon, then pentagon, and well, octagon is in red, pentagon in green, hexagon in blue, and I changed the colors of the pentagon and the hexagon. So we did hexagon in orange, so every other space. Well, right off the bat, are you seeing something? I noticed even with the original pentagon and that last hexagon, there's a little bit of a gap. But let's try to put that pentagon in and go ahead and put those in. And is that matching up? It's not, right? There's lots of overlap in here. So Myra's figure is not a vertex figure. So next we're given this shape. And we have the line M. And remember, lines have arrows. They keep going for infinity, both directions. And then we're given some points and some line segments and some arcs. So first, we're going to look at triangle QPT, and it says that it's congruent to triangle SPT. So what are some things that we see about each of these triangles? Well, what we notice is the line segment for QP is congruent to the line segment for SP. Let's see. And you can see this better now. There's the single lines. Here you'll notice this is indicating that these two line segments are congruent. And then down here, QT and ST are congruent to each other. What else do we see? Well, we also know that PT, line segment PT, is shared by both triangles. So if all three sides of the triangle have the same measure, then that lets us know that the postulate for this triangle is side, 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 or SSS. And that what happens there, it says that if all three sides of two triangles have the same measure, then the triangles themselves are congruent. So the triangles, because all three sides, line segments, have the same measurements, or have congruent measurements with the other triangle, they are themselves congruent. So next we're looking at angle QPT, and it's congruent to angle SPT. Let's see, is it coming in? Here we go. There's SPT and that angle. So what else do we see? That is a triangle, right? We're looking at this triangle. What we know are side QP, which is a line segment, and SP are congruent. We also know that line M is a straight line that is shared by both triangles or both angles. And P is divided down the center. So because the angle QPS, big angle, is divided down the center, and that gives us those two individual smaller angles, that lets us know that angle QPT is in fact congruent to angle SPT. The next thing we're looking at is triangle QPV is congruent to triangle SPV. So what's going on with this one? Well, once again, we have congruent segments, right? QP, congruent segment SP, and we have the shared line of PV, and we just figured out that the angle of QPV and the angle of SPV are congruent. So that lets us, we use the postulate side angle side because it has two sides of the same length and the same measure, which means they're congruent, and we have the angles are the same, congruent angles. Next, we are looking at angle QVP or PVQ, and it asks us, how do we know it's a right angle? Well, because line M is a straight line, and anytime you have a horizontal line that is intersected by a vertical line, that angle is always 90 degrees. Now, we are told that we have a pentagon that is inscribed into a circle. And if you see here, we see penta, P-E-N-T-A, 5. Clever, right? Then we're told that there is an equilateral triangle that shares the same vertex P. So they have a common vertex of P, and that is also inscribed inside our circle. And they have a center point. The circle has a center point of O. So where do we go from there? We need to find the angle of NOQ. So where do we even begin, right? I looked at this and thought, wow, my head hurts already. Work with me. So let's start. Let's take everything else away. We have the Pentagon inscribed in the circle, and we have our central point. The first thing we're going to do is give it some spokes. We're going to go from our central point, and everywhere that the Pentagon touches the circle, we are going to draw a spoke. And that's what you see here, right? So you see central angles. Well, what we know is the sum of all those central angles, the sum is 360 degrees. Well, how many do we need to divide that by? 5, right? There are 5 angles in here. 1, 2, 3, 4, 5. So 360 divided by 5 is 72 degrees. So let's keep that handy. Let's go on to the next one. So we're looking at the triangle, equilateral triangle. We're going to do the same thing. We have that central spot, and we put out our spokes. Well, this time, there's only 3 spokes going out, and that gives us 1, 2, 3 angles. So we divide 360 by 3 and gives us 120 degrees. Now, we're not done. We have to take both sets of information and put it together. So we take 120 degrees and subtract it by 72 degrees, and that gives us 48 degrees. Well, 48 degrees is not our answer. So let's go back to our original problem. And when we put it back together, we need to remember that P is our common vertex. But if you draw a line, right, because we had our radius from the central point O to P, that's our radius. Well, if we extend that out, we get the complete diameter. That diameter divides both the pentagon and the triangle completely in half. So now we're going to take our difference of 48 degrees and divide it by 2, and it is equal to 24 degrees. So the angle of NOQ is equal to 24 degrees. This one's fun. We have Jenny, who is looking at this beautiful, amazing cliff. And while Jenny's looking at this cliff, we read our article, our word problem, and it says, it gives us a whole list of information, right? Exactly what she's doing. She's doing some calculations. So what we know from our problem is that from the distance from Jenny's eyes to her ruler is 2 feet. So there's the ruler's 2 feet in front of her eyes. Then it says that when she's holding the ruler out, the difference between the marking of where the bottom of the cliff is and the top of where the cliff is only 1.5 inches. Then what's Jenny's distance from the cliff? Well, she's a 1/4 mile from that cliff, right? That's where she's actually physically standing. The cliff is a 1/4 mile away from her. What else? What other information they give us? They tell us that 1 mile is equal to 5,280 feet. So now let's work this out. The first thing we need to do is realize that there's two types of triangles in this problem. First is that initial, Jenny standing looking at that cliff, and from her eyes out to the cliff, right? So you're looking out this way. You're seeing the top and the bottom. That's a triangle. So this is what we get, this large triangle. That's the first triangle we have to think about, we have to consider. The next one is the distance from, it includes the distance from Jenny's eyes to the ruler, right? So as she's going out to look at that cliff, it has to take in the ruler, right? So this triangle here from Jenny's eyes to the ruler is one triangle, and then we have the large triangle as she's looking at the cliff. So what is our formula? Our formula is distance between the ruler markings divided by the distance from her eyes to the ruler, and that is equal to the height of the cliff divided by the distance from the cliff. So let's input our information, our data. So the distance between the ruler markings, so the difference was 1.5 inches. Then the distance from her eyes to the ruler, remember she was holding that ruler out 2 feet. So we're going to divide it by 2 feet, and it's equal to the height of the cliff, which we weren't told that, divided by the distance that Jenny is from the cliff, and that is 1/4 mile. So now we need to make sure that all our measurements are in the same format. So we're going to convert the miles and the inches into feet, right? We need some regularity. So here we take 1.5 inches and divide it by 12, and that gives us 0.125 inches divided by, feet. Hold up. 1.5 inches is equal to 0.125 feet divided by 2 feet, right? We already know she was 2 feet away from her ruler. And that is equal to the height of the cliff divided by, well, in this case, we have to take what was originally, what's a mile? 5,280 feet. And we're going to divide it by 4 because she's only a quarter of that distance. She's only a quarter of a mile. So we divide it by 1,020 feet. No, 1,320 feet. Wow. I'm off my game tonight. So now we have to multiply both sides by 1,320 feet. So the height of the cliff is 0.125 feet times 1,320 feet divided by 2 feet, which that gives us a height of the cliff as 82.5 feet, and our instructions wanted us to round to the nearest whole number. So the height of the cliff is approximately 83 feet tall. Thank you for joining me today, and I look forward to seeing you next week. Thank you.